right, that's good. All right, take it away, Michael, whenever you want to go.
Cool. I am going to pull up the chat just to see questions. And can everyone see the title screen?
You're all good?
Yep. So welcome. So what I am going to be teaching you guys is the basics of reverse engineering and exploitation. So this is going to be a lot. This is going to be at a very high level. I'm going to teach you a lot of like the things that you're going to need to know to learn an in-depth. To learn it in depth, it will take practice, but this is at least to help you get started, and this will show you everything you need to get started. So, a little bit about me. I am I'm a grad student at UMD. I also went here for undergraduate, and I also work as a software engineer, doing a lot of C, Python, and some web development. I do some reverse engineering as well, and outside of doing software engineering and reverse engineering, I do a lot of CTFs and dev projects. I'm also into following the latest and greatest in entrepreneurship. Baseball, I'm very big into baseball as well. I don't know if you can see my catcher's bag behind me, but I am still playing baseball, and I also am big into music and stocks. And here's my contact information. I won't go through this just because you will have access to the slides later. And this is just a simple agenda. So I'm going to go through some definitions so you have a clear picture of what reverse engineering and exploitation is. We'll go through then how files are compiled. We're dealing with compiled files when we're doing reverse engineering and exploitation in this case, since we're focusing a lot on the C programs throughout this presentation. We'll also go through how the memory is laid out, so how things work within memory, how things are stored in memory, some analysis and assembly techniques, and then we'll go through some vulnerabilities and then some tools that you can use to actually get started. So to get started, what the F is PWN in reverse engineering? This is probably the question that everyone has when you first get started in this. So let's start off with the first definition. It's magic. I think we all know it's magic, but we're going to go deeper than that. So reverse engineering is a process of extracting knowledge from engineered artifacts. In this case, we're going to be focusing software engineer. We're going to be working on software. So we're going to be extracting knowledge from software. Binary exploitation is the process of subverting a compiled application such that it violates some trust boundary in a way that's advantageous to the attacker. Most of the time when we talk about this, we're trying to get some sort of shell or some sort of information. And usually in our case, we're looking for CTF flags. This can be different depending on who you are, who the attacker is technically. And some words of caution through memes. One does not simply pwn noobs. When I say this, don't pwn anything that you're not allowed to. So don't go pwning your friends or anything like that. And then the second one I thought was just funny, but this is just saying don't spend all your time focusing on reverse engineering. Spend an hour and a half, take a 15-minute break, then come back to it, or work on another task. These are challenging problems. So you want to spend a short burst and then take a break. So let's start off with seeing how files are compiled, and we're going to go through the header. Because the header, which is the beginning of a file, contains the blueprint to the program you are analyzing. So we're going to focus on ELF files because you're going to generally run into Linux, and you're going to generally run into Linux when doing CTFs or most practice problems. So this is the best way to get started. So let's go through this a little bit. So the ELF header contains data about linking and execution. So generally this is data about what are the necessary files or things that or information that is needed for the operating system to actually execute this program. This is just some metadata about what's going to be happening, essentially. So the program header table is essentially an array of entries where each entry describes a segment or other info in regarding the file. So what is a segment? These that are being pointed out now are the segments. So segments either contain code, in this case that would be the text section, or it could contain data, which would be the read-only data, and the data section. And the section header table has all the information necessary to locate and isolate each of the file's sections. So in a sense, a lot of metadata. I don't expect you to become a master of this by the time we finish. But this is essentially, if you need to get some information about the file that you wouldn't otherwise know, you would start here. Does anyone have any questions before I go on? Does anyone have any questions before I go on? I guess not. So I'll start moving on. So let's go a little bit deeper into each of these major sections of the header. So the ELF header, some important things I like to point out here are like the entry point address, the entry point address, the magic, the class. So what this is saying is this is describing how this file is compiled, how this program's starting, and many other important pieces of data into it. I'm not going to go through this one by one just because there's a lot in here and not everything is necessary, but this is that's essentially the big piece. And on the left side, you could see a lot of how this would match to how you could read this through C. So if we go a little bit further, we could see that the E indent, the E ident refers to the magic, the type, and the entry point is pointing to the address. So this is just something to keep in mind. And if you saw above, you can use readelf to read the ELF header from any point. So take a look, make sure to look at these, and these are useful commands to say, I want to get this particular part of the header. The section header, so this is the section header. What is it? It is a well-defined header that gives information on a section of a binary, which is unstructured. So in general, what this is saying is we're defining a structure, making a structure to it, and we're giving a description of it. So and this is helpful for the operating system to know. And like I said before, some of the most important ones are the text, the global offset table. We'll go into this a little bit later, and the data section. So the program header indicates how segments required for execution are to be loaded into virtual memory. We will get into virtual memory a little bit later, but what this is trying to say is the program header is laying out a lot of different, and the program header is laying out where things are going. So essentially, if we want to set, and if you see in this picture, a section refers to a segment. So in the sentence there are, this is saying, okay, this section is referring to this segment over here. And it's almost like a table in a sense. And also a lot of disassemblers will help reconstructing it and make it easy to view as well. And the last thing I want to point out here is I want to show some of the similarities between different file formats. So on the left, you have the PE file format, which is the most common one used in Windows. I'm not going to go through the different sections, but what I want to point out is some of the similarities. So here we can see the PE file header. This is similar to the ELF header in this case. This is similar to the ELF header. And we could also see that there is the text section header, which, as we mentioned in the previous slide, that will relate to the text section itself, or the text segment. So there are a lot of what I'm trying to say here is there's a lot of similarities, and when you start to understand Folio 1, you can get a picture, and a lot of patterns come up, even though there are some differences. And that if you want to learn more, most of this information I've taken are from Drake MP's slides. So he's actually part of the Cybersecurity Club. These are two of his slides that I took some information and presented it here today. And so before moving on, does anyone have any questions about the header? And if you want, you can unmute yourself and talk if you're allowed to.
I just enabled it.
Okay. Going once, going twice. Okay. So let's start talking about the memory of, or how a program uses memory. And this is a big case. This is a big part of it. So remember how I was saying virtual memory is an important thing? So this is why virtual memory is important. So virtual memory makes it easy for the program to use physical memory. So in a sense, we can use, rather than a program using the literal address in memory that's using, it creates virtual memory. So that way we could say, oh, for this program, I want to go to the beginning of it, or which is in this case 0. One way that we achieve this, and probably the most common, is through paging. It organizes chunks of memory into separate pages, which are typically between 512 bytes and 8 kilobytes usually. So what that means is often when I need to put in some data at a particular, I need to store some data. When we put in some data, we put it into a page, and we mark that page as being used by a particular program. Often the case is the reason why paging exists is the fact that we have this is a lot faster to access, mainly because we don't have to go through we don't have to go through everything. One way we achieve this is a page table. So what a page table does is it groups a bunch of pages, and it stores the pointers. It stores the pointer to the beginning of that set of tables into a particular page. So basically, think of a page table as a page pointing to other places in memory. And this at the bottom is an example of how this can work, or how a lot of the time this works. So usually there's a page. There's usually the beginning of an address points to another place, and then after that, once we're trying to find the offset, we generally just look for that offset. Um, so another important concept is paging algorithms. So I just know that it's there's three different kinds. There's first in, first out. So and there's first in, first out, least recently used, and random. I don't want to go through too much of this just because this also gets into algorithm or operating systems a lot. And yes, there is FAFO, but we'll there is other algorithms too, but we'll stick with there. But there's a lot you can Google too. So I would spend some time looking at this because this is useful knowledge, but not completely necessary. Not completely necessary to get started. In terms of reverse engineering and exploitation. So just to go over some of the memory layout, and we're going to focus on 32-bit. So memory is laid out into different chunks. So in 32-bit memory, the maximum we could have is 4 gigabytes of memory. And 1 gigabyte is dedicated to the OS kernel stuff. Often what we're going to work with is stack and heap. Stack is, so these are the two places where we generally put data in. And then there's also two other sections, that BSS section, which contains uninitialized static and global variables, and the data section in memory, which contains initialized static and global variables. So usually what a global variable would be a variable defined outside of a function. So if that's just to make it clear, and static would be a keyword that allows yeah. So just to move on, so going into the stack itself, so the stack is defined. So the stack is generally going to have. So generally, we're looking at a function in stack. We're going to be looking at we're going to be looking at the base pointer. So that's what EBP is. EBP is going to say, here is where I'm going to start. And then above it would be our return addresses. And then below it, we have these XX, YY, ZZ, and ABC. So what those are, in particular, is going to be data, but different kinds of data. So if we're assuming integers, and this is obviously the Intel architecture too, anything below the EBP, or like, let's say EBP, subtract the address of EBP by 4. Well, we're going to start with local variables. So this is generally local variables or local integers. And above it are going to be the parameters to the functions in general. There some other things that you want to consider knowing, since that is a very simple case, is data structures. So different data is going to be different size in bytes. So and then there's also pointers are going to be particularly useful when you're reversing, because you need to know where everything is going. Pointers point to different addresses different addresses in memory. And then you also want to know the basics of like structs, linked lists, and arrays. To give you an example on the right, we have a parameter, and then we have a parameter up above, but below it we have a local variable that's an array of integers. So in this case, each one is an integer. So in this case, it's going to take, if we looking back, we see how EBP minus 4 is going to takes a local variable. Well, in this case, it's going to take element in the array. So you could consider R0 to be, since there's a variable above it, you can consider R0 to be EBP minus 8, R1 to be EBP minus 12, et cetera, et cetera. So, and then also there's also with data smaller than, to go back here, if there's data that is smaller than, if there is data that is smaller than an integer, you could have a character that takes one full block. So what will happen is it'll take 1/4 of this, and the remaining 3 are going to be empty if you're only saving a character. So just keep those things in mind. This is a lot. There's a lot that goes on, and there's a lot of changing things that happen in the stack or how memory is stored. But if you remember the key things, that EBP is where you start, just above its return, the return address. So when we say return, it goes to that specific address. So this is ret is an address. Parameters above the return address and below EBP are variables. Those are the key things to keep in mind. And then the last thing I want to explain in this section is registers. So we looked at one register already called EBP. So it's the base pointer, and generally this is for saying, okay, I'm starting at this section in the base. But there's others that are used to store memory, and each one is 32 bits or 4 bytes, just like in the case of 32-bit processors. In 64-bit memory, which instead of EAX, it would say RAX, RBX, RCX. It would double the size, so it would be 64. It would have 64-bit registers in total. So why do we have this? It is extremely fast to access because this is as close to the processor as it's going to get. But the downside to this is it doesn't hold a lot of data. So that's why we have register. That's why we have memory and disk. So you can also, as you can see here, you can also access portions of registers too. So if you want to read the first half of EAX, you can say AX, or if you want to read a quarter, AH or AL. So those are, and you will be working with registers a lot if you're going to be reading assembly. So knowing registers is very important in terms of reverse engineering and exploitation. Before I go on, does anyone have any questions? Okay. So now we're going to start getting into the good stuff. We're going to talk about static and dynamic analysis. So what are they? So static analysis is learning how programs, I should say, there's a typo in here, but learning how programs behave without running the executable. So in this case, it takes reading a lot of assembly, requires a disassembler, and often framed as the cool way of reversing, and should be, I think it should be the last resort unless you have source code. So if you have source code, you don't necessarily need a disassembler or to do static. You don't need a disassembler, but you can immediately see what's going on. But generally in CTS, you're probably going to go straight to static analysis. Sometimes you're going to have to do dynamic analysis, which I think is the more common way in reality. So dynamic analysis is learning how programs behave by running the executable. So often there are tools like strace and ltrace where you can see how how many system calls there are, or library calls there are. And, but often you're often going to use this with debugger. You're often going to use debuggers too. And this the reason why I like dynamic analysis a lot is it can help pinpoint errors and spots for further analysis. So you can start off by doing dynamic analysis, and once you know where you need to go, you can go back to static analysis. But so that it's very helpful to have knowledge of static analysis to complement as well. So assembly, I highly recommend learning the x86 and ARM architecture. It's required. So this is required to do a lot of reverse engineering. And there's two syntaxes that you need to pay attention to. Into the Intel and AT&T syntax. Some examples of this. So we're going to dissect the move instruction. So in move, we can see that with Intel we have move EAX comma 1, and then in AT&T we're going to have move L $1 comma percent EAX. What's the difference? So the difference is they're both doing a move instruction, but what they're both doing is putting 1 into EAX. The difference between AT&T and Intel is that Intel, you put the destination first, and then any other arguments after the fact. In this case, we only have one argument. We're just moving 1 into EAX. AT&T, this is backwards, and also they are defining, like, they're using $ and percent to say this is either data, this is an address, this is a register. So knowing how to use both is very good. And also some things that I highly recommend is just go out and practice and use the processor manuals in Google a lot, because you're going to the best case of learning how to do is learning how to read assembly is by doing RE problems, and just Googling every time you don't know something is probably the best way that I went out and did it. So in that case, I have some actual things to disassemble. So there are a few things that I just want to say. I want to just also make clear I have 2 snippets of code in assembly. So when we're looking at this is going to look like a lot, but you also want to know how the calling conventions and the patterns. So in this case, we're using what's called cdecl. So that's this. What that does is it. I didn't prepare a slide for this, but for cdecl, it's often going to push arguments onto the stack. It's going to push arguments of functions onto the stack. The caller is going to make room and say, set up my function call, things like that. And it's basically the way that the program understands how to work with functions and code. So in this case, what I particularly want to focus on in this snippet is, so this call to A to I. So we can see that this this call to A to I is taking a character and then returning an integer, or a string. Sorry, it's taking a string and returning an integer. So So what you want to, so the big thing is this, so this, so it's, here we go. Yeah, so it's in the beginning section, it's taking, that's, it's taking the string, uh, it's taking the string, this is all this, it's taking the string and putting it onto the stack, essentially. So take, um, and then, and then afterwards, it's taking, so in here, after A2I is finished, it's taking EAX and return and putting it back onto the stack. So when you're put, so essentially it has to, the big thing is like what I was saying before, it has to make room, so it has to put it onto the stack in order for it to be a parameter, and then it returns the integer into the register EAX. The other, there's also a snippet of the final code, but I'm not going to spend too much time going over this. I think this is best. It's best to. This is a great way to practice seeing what's in here, or seeing what's in here and seeing how what's actually going on. Um, also, before going on, the last two things that I want to cover is, so the first four instructions and the last two instructions. These are going to be common because these first four are the prologue, the last two are the epilogue. Each function has them. What they do is they actually set up how much of the stack is, it needs, and then and then the epilogue finishes it up, cleans it up, and fixes everything. So that way, when it goes back to the previous function, it knows it leaves off, it goes on from where it started. The particular ones are the set that are big indicators are the stack pointer. So if you see here, it's subtracted 20, 0x20. So 0x20, which is 32. So that means there's 32 bytes. There's 32 bytes being used by the function. So this could, if we're talking about strings, this could be one function that is using 32 bytes or less. It could be multiple integers. So that's a big one. There's also other ways of representing this, but if you Google it, so when you spend time on this, Google epilogues and prologues and see how the different ways of being represented are. So before going on, are there any questions? Going once, going twice. Okay. So let's get to the really good stuff, exploitation. So the first one I want to talk about are buffer overflows. So what we're trying to do here is we're trying to overwrite the desired part of memory. And it's caused by unbound standard input. Generally, the functions we want to look for are get, printf, fgetS. So if in the case of we want to read from a file, and it can be both stack and heap based. So the question for you is, how are they different? And so and below is an example of what I mean by this exploit. So first, and I will go over both, but take some time to think about it first. What's the difference? Um, first, the things to look for, if we are given source code, is this gets uh, buff. So essentially, this is saying put anything from standard input into the buffer, and this is going to just keep reading until you're finished. And if it's more than 12 bytes, good for you. You can put 16 bytes onto the stack, and it doesn't care. So a visual example of what I'm talking about. So let's say we're putting in a buff. Let's say we have input into Z, um, and we decide to write, and then we decide to write a whole bunch of data, much more than what was allocated. What we end up doing is this: we can write all the way up, and usually the goal for this with buffer overflows is we want to overwrite the return address, because if we are able to overwrite the return address, we can actually control how the program is executing, and which could be shell code or another place in the program. So another form, and before I actually go on, the difference between this and heap overflows is with a heap overflow, you're overwriting heap, and heap contains data, not so much return addresses or things like that. So generally, some ways we can do heap overflows and actually exploit it are overriding function pointers, use after free. So if we free memory in the heap and then we use it after the fact, then we can through the fact that we are doing through it, and one way to do it is through heap overflow. Then we have we can attack it essentially. So another way we could do this is through format strings, or another vulnerability is format strings. So in general, if in 216 you probably have learned that you have to have in this case the first one, the %s %s argv1, or take it whatever input you want, print it, whether it's in this case is a string. So what happens in the case that we do the second one, printf the argument? What we end up doing is we can essentially tell the user can use format specifiers. So it can use like %x, %s, %p to essentially hijack the program. And one example of a malicious one is %n, or the malicious one is %n. It stores the number of bytes written to the screen thus far to an integer pointer on the stack. So an example of this attack. So let's say we have this standard input here. So ABCD, %P, %261, $P, %4n. And another, this should be %4 $n, like the 261. So what this little piece here is saying is we can put this number $sign is saying I want to put it in the 261st. I want to read from the 261st place. In the case of %4 $n, we're saying write this number in the execute this line below here. So it's taking ABCD and little endian. So, and this little endian mean backwards. So D is 4-4, C is 4-3, B is 4-2, A is 4-1. And since we wrote 35, but since we wrote 35 bytes to the screen, that's what we're going to do. And I'll answer the question. I'll answer the question in a second. So this is the big. So this is so yeah this so in this case in the format string, we can essentially control what kind of input is being put into there and essentially hijack the program. And then I see a question from Darren saying, does it matter that you overwrote the EBP? In the terms of an attack, and I'm assuming this is for buffer overflows, in the terms of an attack, not so much. This is, you can so EBP is useful. So you don't, so the simple answer is no. You don't need to matter that you overwrote the save EBP. The bigger one you care about overwriting is ret and any data, any variables that you're overwriting are the big things that you care about. In terms of format string, does anyone have any questions about format string attacks? Okay. So timing attacks, timing attacks are based on either delays or inconsistencies with execution time. The big goal is if we know how long it takes for the thing we want to execute, we can use that to attack the software. So essentially, if we have inconsistencies of, if it takes, let's say it takes 5 seconds for a program to crash, but 10 seconds for it to return successfully, we can take advantage of the fact that it crashes 5 seconds to potentially do a vulnerability to a system. And for anyone, so let's take a second actually for you guys to answer some questions. Which one of these is vulnerable? I'll just feel free to put it in chat, whether it's the first one, the one at top, or the second one, the one at the bottom. Oh, yeah, we could do that. And then I'll answer the question by Dewey. How do we? Oh, here at the top. How do you actually create a poll? Oh.
I could be wrong, but I think maybe Vanya is the only one who can do it. But I could be wrong.
What do you need?
To make a poll?
Oh, sure.
Yeah, which
Happy.
one? Yeah. Yes. Which one is vulnerable? First one or second one? And to go back to, and I saw a question from Dewey. So the first one, the reason why the first one is safe is whatever input from argv1 is happening, whether it's this exploit or this exploit that I have at the bottom or something else, it treats it as a string. So it's saying the input I'm having is a string. The input I want put here is a string. What this is saying is, it's basically saying putting in the first one. So like how we said, we had these format specifiers. So you could put in format specifiers, and this tries to read off the next point into the. So it tries to read the next parameter and assume that it's and it tries to assume that it's a like it's an argument to printf like this one. So that's basically why. So basically, when we have %p, %p, percent %p here, %p, it's saying I want the pointer. So %p is pointer. So it's saying I want to read where I think the argument is to printf. I want to read the address to that. Then I want to read the next address after that, etc., etc. With the format specifier, it says I want to read the 261st argument of printf, where what I think is the 261st address, and give me that address. And this is saying, write the number of bytes I have written so far into the fourth argument of printf. Yeah, and I'll go. You're welcome. Yeah, feel free to just, if you have questions, this is also a good time to do that. And I'll give you guys a couple of minutes. I'll give you guys a couple of minutes just to read the code and figure out which one is potentially vulnerable or not. And I will. Let's see. How many participants we have? 1, 2, 3. I'll give another minute just so I can get some water. All right. I think everyone has voted. So in this case, the potential vulnerability. So the potential vulnerability is the top one. So the reason for this is, if we were actually trying to perform a timing attack, I don't think there's actually a vulnerability, but this is just in case to show timing. If we look at this return false inside of the for loop, we're terminating in the middle of a for loop. In this case, in the bottom case, this might be more efficient. Because this is less efficient because we're looping through everything before returning. But what we're doing is ensuring or guaranteeing that the execution is always or the return always happens at the end after the for loop. This case, you could potentially just do, iterate once through the for loop, and let's say the length is 5,000. You can iterate through the first one and hit this case immediately, and you're done. So those are some things that you want to look for. Yeah, and Darren has a good explanation of it too. So if you want to read it through chat, if you're still a little bit confused, Darren has a good explanation of it. Linking attacks. So I mentioned this briefly at the beginning. So I've mentioned linking briefly in the beginning. So what is it actually? So when we're compiling a program, we're not necessarily when we're we're not necessarily bringing in every single possible function in order to run the code. Some functions that are very common, like printf, so printf, gets, are generally linked in into the final binary. And sometimes the user actually creates, and these are called libraries. Sometimes this is also created by the user too. But what we generally, but what are the benefits of this? It reduces the size of the program and reduces compilation time by a lot. If you want to, in GCC, if you want to just say, I want to compile everything in, there's a flag for that called static. And there are some use cases where you want to guarantee the same kind of execution, but the same library is being used, or the same way printf is being used. Let's say we want to use printf in the same exact way as my computer is doing it. That's why the static flag is there. So some files to look for are Linux and Windows, or in Linux is .so, in Windows is .dll. So why are these useful? So on top, there's a type of buffer overflow that you can do, that you can attack with this called ret2libc. This takes advantage of the libc.so, but there's another thing that I want to talk about. It's called linking attacks. They're not as common as in CTFs, but they're an important exploit for you to know. So one example of this is like the LD preload. What we're trying to achieve is we're trying to overwrite the behavior of a function we're expecting to be called in a certain way, and we're using it with our own. So in the case that in my class, he used this. It's hard to see in this image itself, but this was from my class, RE and PWN 691. What he is doing is there's a string compare. There's a string compare file that is taking the string. It's so he's compiling. So he's compiling in. He's compiling a. So he's compiling a file. So what he's trying to do is essentially take the string compare hijack and essentially use the environment flag LD preload to essentially change the behavior of the string compare target file. So the fact that we're loading in string compare hijack.so before running the program, there's some unexpected behavior in this library file that allows it to say green light. So in a sense, there's a function that it's overriding in string compare target and with a linked function in string compare target. So this could be printf. This could be some function that he created himself. But generally, that's one example of it. There's other linking attacks, but it's not the main focus that I want to go through. But I just want to share what's there. Are there any other questions about exploits before I go further? Okay. So that's what I want to talk about for exploits. So I want to share some tools to help you guys get started on this. So debuggers. This is, oh, I just saw. what's the defense against linking? Trying to remember what the defense is. Why am I drawing? I think the defense. I think the defense is through the compiler itself, but I don't totally. That's a good one to remember. Yeah. Yeah, I think the defense is through the compiler or operating system. I'm not 100% sure. Yeah, and also Vanya has some good points on the LD preload. I had some good points on LD preload. And yeah, that's a very good point. It's not all OSs implement the LD preload, so I just be aware of that. And this is also a security measure that they use. I'm trying, but yeah, I'm sorry, I don't remember totally the. Yeah, I don't totally remember the defenses. Yeah, yeah, no. Okay, so some debuggers. In Linux, so debuggers allow you to see parts of. So debuggers allow you to see the. So yeah, the debuggers allow you to step through a program and see what's actually happening. In Linux, use GDB. That's the best one to use. And there's also, I highly recommend getting extensions for it. So what I am showing here is PETA. I call them extensions. I don't know if that's what they're actually called. What I have here is PETA. So what PETA and Geth is very similar is it has some exploit techniques that besides showing the registers where it is in the assembly and the stack, it has some cool techniques that allow you to make it easier to exploit. So often like creating patterns of really long strings, so that way when you're figuring out, okay, how long do I need to make my um, um, in order to see how long a buffer overflow needs to be. That's a very good way to do it, and often that will pop up in the registers. Pwn debug I have not used a lot, but it's a very popular one as well. For Windows, you're going to want to use WinDebug. It's a little bit more of a learning curve to use, but it allows for the same features as having like GDB and PETA without the exploit. So you can see the disassembly, the registers. Once you get used to it, it's very nice. But I highly recommend starting with GDB and PETA and Linux. Windows has a lot of extra things that is a lot of the time confusing. Disassemblers. This is what it obviously means. It takes a program and disassembles it. In from to assembly, and in the case of Ghidra, you can decompile it into C code. This allows you to step through, or see what's going on in the program. I have a snap of binary ninja here, but it also, you could do things like patch. You could patch, do a lot of symbolic it can help with symbolic execution. We're not going to go through what symbolic execution is, but in this one, but that's like a tool like anger. It helps you simulate executions to find your desired result. The other tool for CTFs I highly recommend for exploitation is Pwn tools. it helps you create exploit chains very quickly. And this is one that I use for the return to what challenge in, I forget what CTF this was, but it makes exploitation a lot easier. And you can also use it for format strings. You can also use it for analyzing the binary, but it also, in the concept of return-oriented programming, which is essentially hijacking return, it allows you to build out those for you. If you want a little bit more resources on ROPchains, feel free to message me. There's a lot going on. There's a lot happening with ROPchains, and it takes time. It takes time, and it's a little bit more complex way of doing buffer overflows. And this is the link to actually download Pwn tools. And then I also compiled a really big list of tools that you can use as well. So this is partly built-in ones, and then some that are commonly used on the web. Does anyone have any questions about the tools, or any questions about tools that they've heard of?
So I don't know if you ever went over this, and I've never really known myself. So what is the difference between strace and ltrace? I'm generally familiar with them, but not specifically, you know.
Right. So strace goes through system calls in particular. So hence the S. And then ltrace specifically is calls to library functions. So essentially, if you see like external libraries like called like, let's just for example, libc, like I don't know what function libc. But yeah, essentially, like if you want to see if there's other libraries being called that you want to use, use ltrace. If you want to see what system calls are being used, so like, is it printing two statements? Is it exiting? Things like that. Those are the big difference between strace and ltrace.
That makes sense.
Yep. And even just for debugging, I've used strace and ltrace a lot. These are useful tools to know, in particular. And yet, I do say, I think reverse engineering has helped me become a better, debugger in general. Any other questions or? Okay. So I've compiled a list of practice problems. So this is under a GitHub organization that I created. These contain, a lot of them are from UMD CTF, but they contain some easy to medium range Pwn problems, and then easy to medium range reverse engineering. I think there's a few from I think Meta CTF too that I was working with. So those are very good practice problems for you to just get your hands started. And feel free to ask me questions if you're stuck on them. And I know there's a lot of exams going on, so I don't blame you if you don't get to them right away. Some other places to learn more. The first link is a link to a binary exploitation course given by Rensselaer Polytech. This has everything you need to know about binary exploitation in a lot more depth. And they break it down very well as well. So that's also very good. I highly recommend that course. I've learned a lot from that course, and also some of the courses I've taken here at UMD. Mainly for me, I've done it through the professional masters. And yes, CMSC 389R. And then also I've learned a lot from Drake, who's in the class, and he has from his teaching, he has a ton of slides, and I pulled some stuff from his slides too. So that's a very useful option. And I'm going to create some more slides too. So I'm starting to build one on blockchain itself. And I'm just going to create some slides and put them on here so that everyone can see and share. And there's also, just do some CTFs and read the write-ups. That's the best way to learn. There's some that are beginners, some that are more advanced. Just keep trying it, and it'll be a struggle, but the more you practice, the less it's going to feel like magic. That's for sure. And funny enough, in the reverse engineering course I'm taking right now, he was saying the exact same thing and explaining how like practicing for 10,000 hours makes you like an expert or something like that. I don't remember, but practice is the big thing. And then some works cited. So this is just some slides from Drake. I borrowed some information from my current reverse engineering teacher, Alan Hazelton, and then on the linking stuff in particular, my binary hacking C programs and Unix binaries teacher taught me a lot of this. So I'm giving credit to him. And does anyone have any more questions? And feel free to unmute your mics now. This is everything that I had to share.